Our next speaker, again, leaves very little introduction. For those of you familiar with a book called The Hitchhiker's Guide to the
Galaxy. Hitchhiker's Guide to the Galaxy.
To the Galaxy?
Yeah.
There was a conclusion that said that life, the universe, and everything equals 42. And Richard is going to tell us now that 80 is the figure we should be looking at. So 80%, the most understood number in this traffic and traffic simulation.
Absolutely, thank you very much. And actually, before I start, I'm going to make one small comment on Lutfi's presentation, if I may. Where's he gone? Oh, he's hiding there. Yeah, so I'm always entertained by Lutfi's presentations, even if I don't understand them, but I did follow most of that one. For those, I think the people whose ears should have been picking up there were the people who do IoT, where you put accelerometers on the top of the cars. So, because what we're doing, ultimately, is just extrapolating what the traffic demand is in the building from a sensor that you already have in the building. You've already put on there. So I think it's all a bit academic and stuff, but actually does have some real world application. And I look forward. When did you start doing this work?
3 years ago.
No. When we were.
Oh, this was 1990.
Yeah, so I got very excited by a paper that Lutfi presented in 1990. And he's still working on the concept for me.
That also means you haven't got to carry accelerometer.
Yeah, absolutely. I don't want to carry accelerometer. Anyway, I'm going to talk about 80%. Obviously, I'm talking about traffic analysis simulation, but I know that you're all desperately excited by this because it is the most interesting topic in the lift technology world. Ultimately, we're looking at how effectively we can manage passenger demand at peak periods. So we've got lots of people, we're going to move them, and we've got to do some calculations on that. And one of the key things is how many people can we get in a car? Yeah, so we're going to start off with that. It requires an assumption when we do calculations about that. And when I started, and this was, I put the 1990s, actually it was the 1980s, but 1990s more professionally, working on simulation and calculation and things like that. And what we did is we said, and this was when I was at Arup actually, dividing the lift capacity, 1,600 kilograms by 75 kilograms per person, and we get a 21-person car. And that's basically how I decided how many people you got in a car. And most of the people will know Gina. If you don't know Gina, talk to me about Gina afterwards. She was sort of the grandparent of traffic analysis in the modern world. And she told me, "You're wrong, Richard." And in her inimitable style, you cannot get 21 people in a 21-person car. And of course she's right. And this is what I looked like back then. Yes, Dr. Barney. Yes, Dr. Barney. But I have an 80% factor. Here's the 80%. Yeah. And what I do is I say 80% of 21 is 16.8. So I only think you get 16.8. And that's my excuse for it not actually fitting in. So that was my understanding at the time. And then she said, "You're still wrong, Richard." And she said, well, actually what happens as the car gets larger, you have less platform area per person. Do people know that? Yeah. Aware of that? Yes. So actually you've got these at the 630 kilogram, that's fine, no problem. But when you get to the really large cars, you've got much less area per person if you're calculating based on kilograms. So the whole thing goes wrong. And I really try to wiggle out of it and say, oh, we can adjust the capacity factor as we get bigger cars. But no, she's right, I'm afraid. She was right. And so that's when I started adapting my calculations to fall in line with Gina. And we've still got the mass over there, but we also have got the area. So the area of the car, that's 3.56 divided by 0.21, 21 persons down to 17 persons, so it's not so big. And of course, then I'm still applying my 80%. What's that 80% for now? It's not about derating, it's something else, isn't it? But therefore, we get down to 13.6 persons. So my calculations were assuming 16.8 persons. Now they're only assuming 13.6 persons, which is a bit embarrassing, really, isn't it? But anyway, Gina, that made Gina feel much better that I agreed with her. She felt I was taught it. And this is a slide from yesterday when we were talking about the development of Guide D. So Gina started the traffic section in Guide D in 1993. And someone, if you were here yesterday, you would have heard me say this. Peter Day, who was in charge of it, asked me to improve Gina's section, and that wasn't received very well. Improve Dr. Gina Barney's work, and that's when we were angry face mode. And as the years have gone by, and these are every 5 years, apart from when she was angry, we've updated Guide D, and we sort of merged together. Sometimes she was right, sometimes I was right, and she quietly accepted it without acknowledging it. But anyway, we do our best. And I thought, if I die tomorrow, you can put this on my gravestone if you like. An engineer is guided by principle, but corrected by truth. I think engineers, that's what we do. We're not like politicians. We don't try and hold on to lies. We should actually, when we learn something, we should change. Yeah. And that gets me to ISO 8132, and there'll be some, and those of us who, actually I don't know if there's anyone here who's involved in the original work with this. This was the battle that we fought, and I've deliberately got a picture of the Joan of Arc there, and that was Gina. And I'm that person behind with my sword. We cannot do it based on mass, we have to do it based on area. Yeah? And we almost got there, but we actually, ISO 8132 in traffic analysis allows you to use mass or area, which actually makes it quite a confusing document because you can use either or, whereas in Guide D, we've just gone for area. So battles that we've had and continue to fight. And the reason I think we won the argument to include area was this one, because actually sometimes the platform area allowed by ISO isn't delivered. We can have a 1,600 kilogram lift, but it might actually not have room for that 3.56 meters because the shaft is smaller. And I did this one measurement, this one job where it was a 1,600 kilogram elevator and it had 2.92 meters square platform area. So it's considerably smaller. And according to the plate on the elevator, it had 21 persons could get in it. When I did my calculation, I reckoned it could get 13.9, and I observed a maximum of 14 when I was doing a traffic survey. So we can make some big mistakes if we're not careful with this. So it's worth getting it right. So having assessed that we need to work out lift capacity by area, so what's the 80% for? There must be something other reason for having 80%. And if what you we actually have to look at other industries and other statistical experts. So this is the easiest example I've found. This is a network capacity. When they're planning for telephones or networks, basically network capacity, what they do is they limit it to about 80% to avoid getting near overload and outages and saturation. Yeah, so that 80% is about not getting too close to the threshold where the whole thing falls over. And to demonstrate that, we can do some simulations. So I've actually got the ISO template here, which is a sort of a 2-hour template, 5 minutes, and I've got a mixed traffic flow we've got running there. And what I've done is I've done a number of simulations, and I've done it at 11.5% passenger demand, 12% passenger demand, 12.5 and 13. And I've done it, ISO normally just does one simulation, but I've done 10 simulations. And if we look at them individually, this first simulation, the demand at 11.5%, I've got a waiting time, an average waiting time of 26 seconds. 12%, I've got 32 seconds. And then at 12.5%, it's 39, and then 71 at 13% demand. So as the demand increases, the average waiting time goes higher. This is my second run, so it's completely separate, different random number seeds when you run the simulation, and you get a different set of results. So I've got 26, 30, 59, and then 151. So that's gone up. That 13% one's gone up quite a lot, hasn't it? Yeah. And then this is the next one. And then this next one. And this one, actually, the 13% is going all the way up to 212 seconds. So it's the higher values are much less stable, aren't they? As the demand goes up, it becomes less stable. And that's to do with the loading. And I'm going to talk here, I ought to acknowledge Janne here, because he actually, Janne Sorska, he suggested we should look at these with standard deviation because it's a good analytical tool. And basically, it's a measure of the variation of a set of values, and that's what it does. And for simulation, we can see how much the results fluctuate over a series of runs. And that's what we're doing here. And a low standard deviation suggests that actually we're nice and stable, and a high standard deviation suggests the results are unstable and not reliable. And if you do that to the results that I've got here, you can see I've plotted it by carload area. You've got 71% carload area. Over the 10 simulations, the standard deviation is 2.2. At 79, I've still got a standard deviation of 2.3. As soon as I get it to 86%, so with the extra 0.5% demand, I'm getting up to a standard deviation of 23.3, and then it goes up to 42.2. So the whole thing becomes completely unstable. So my results for my 13% demand are actually just unreliable. Yeah, so because they vary so much, they're so dependent on the exact generation of the passengers in the simulation. Okay, so ideally we'd have sort of a low standard deviation, about 2 to 3%, less than 5%. And this is a figure I think we might end up using within simulation software to say, okay, well, we'll simulate until we get to that level, or we reject it on the basis that the standard deviation between the runs is too much. It's a nice little measure to see if the simulation is stable and worth doing. And here you can see the lower two lines. They're at 71 and 79% loading, and the top two lines are at 86 and 88. So that's what's causing the unreliable results. So my suggestion, actually, if you're going to do these sort of simulations, and I have actually mentioned this in Guide D Section 4, you actually don't need to do all these multiple simulations. You just need to do one simulation at the demand that you're looking for, and then look at what the loading is. Yeah, and then actually you know that's stable, and you also know if you're above 80, then you're basically on the verge of falling over. If you haven't fallen over, if you're sort of at 50 or 60, then you've got lots of spare capacity. So I would like to flip round it when we come to revise ISO 8132, and it'll be due for, we'll start thinking about it soon. So that's my proposal for that. This is actually what we do within the SIBSI templates. And SIBSI templates are a slightly different approach in Guide D. So we're actually dealing with a transient, so we're going up to the peak of 12%, coming back down again. But what we're doing is we're looking at the loading at the peak. Yeah, so you can see here, we're looking at the loading, and we want to, I thought I'd got an extra slide there, but I'm looking at the loading at that peak. And you can see here that it doesn't exceed 80%, so that's why I'm happy. Application. So there's been an FAQ on our website on how to do loading for years, but I wanted to sort of focus in on it, and I've spent more time in Guide D actually explaining it. So what we're doing basically is when we're doing a calculation in a popular software program, what we're doing is we want to specify the capacity factor as 80%. So I'd have them both at 80%. So when you're doing a calculation, you have an input of 80%. When you're doing a simulation, you have an input of 80%, 100% I mean, and then you look at the results and check they don't exceed 80%. It's a bit subtle. Which is why it needed more than FAQ. So there's a whole paper on it now on why I would take those inputs and look at those results. So to conclude, Gina was right most of the time. Not always, but most of the time she was right. I violently agree with Gina on car loading. This is the way to go, and anyone who disagrees with me, I shall argue as vehemently as Gina on that. It's the way to go. The 80% rule is not about the mismatch between rated capacity and the number of people you get in the car. So we need to use area to decide how many people you can in a car. A secondary check with mass is fine. Actually, the smaller car sizes, that might actually be the pinch point, but it's almost inevitably it's the area. If you've got bigger passengers, so historically what people would do if they were doing hotels or hospitals, they reduce the capacity factor, so you take that 80% down to 40% or 50%, but that's conflating the wrong things. That's not actually the right way to do it. All we do is we increase the area per person, and then you can solve it that way. So in calculation, design to 80% loading. In simulation, allow 100% loading, but check that your average loading at the peak doesn't exceed 80%, and then we're happy. And if you run a simulation and the loading exceeds 80%, then your results are unlikely to be stable. And I get lots of emails, why have I got such high just high average waiting times, and why is it vary so much between the runs? And that's the reason, because the loading is high. Final thought, and this hit me the other day, because I'm becoming increasingly aware that the work that we do in traffic analysis is going to be related to evacuation. So at the moment, the work that we do is to do with how long people wait and how inconvenienced they are and how annoyed they get because it takes a long time to get to their destination. Now we're going to be dealing with how quickly we can get people out of the building in an emergency situation. So it's actually become a lot more serious. So when we start doing evacuation calculations, being realistic about the loading you can get in the car is really important. So that's why I think this is the time to say that's the way we're going to do it. That's it.
Do we have any questions? Adam?
Well, I guess there might be two observations rather than questions, Richard, but always your opinion I seek, always.
Adam is currently on the ISO committee, so you're going to be backing me up on this.
But the first one, I think, is this 0.21 that we use.
Yes.
And its relationship to an elliptical form.
Yes.
And yet we're trying to fit elliptical forms into rectilinear lift cars. And we can say 3.36 square meters, ISO standard, 1,600 kilogram car, divide by 0.21, it's 16. You won't fit 16 elliptical shapes in that rectilinear car.
Yes. Now my 0.21 is not actually based on ellipses. It's based on counting people in lifts.
So your 14 people that you observed in that
Yes.
2.92.
Yeah. So I'm not sitting at my desk drawing ellipses and popping into the car. I'm counting people going in and out of lifts and say that person's not getting in because there's too many people in the lift, and then dividing the area by the number of people by the area and getting 0.21. Actually, it varies a little bit. So if you're in a hospital and you've waited for ages, you can get down to 0.17. If you're in a building where you've got really good lift service and the culture is you don't want to be anywhere near anyone else, it can go up to 0.24. So it varies according to culture and the building, but the 0.21 in offices happens to be actually a good value. So that's based on observation, not on Section 2 of Guide D 2020.
And if I may, just one other observation, observation which has gone straight out of my head. Hang on a second. It was the 80%
Yes.
factor. Seemed to me from your presentation to be a statistically justified number.
Yes.
Not necessarily a human behaviour number. And that
Correct.
piece of, different people will perceive the lift car as full with different loadings.
Yes. Yeah. But at 100% loading, so if you allow 0.21 persons per person, you will at a peak times you can load up to 100%, and that will happen. So the 80% is just coming back from saturation.
Yes. Okay.
Yeah. So, it's taken me years to really work out what was going on because we had this 80% and no one ever explained what it was for. But it's a statistical thing. It's not a derating. We don't want to be too close to the saturation point. Years of sort of, I could never understand why I got these simulations. And you just add a little bit more and the whole thing collapsed. And that's because we're on the edge of simulation. And as soon as we started doing the templates and looking at the loading, we found our results so much more consistent.
Sorry to grab the lens, just very quick one. When you increase your handling capacity and the statistic...
Passenger demand rather than home capacity, yes.
Sorry, yeah, then your standard deviation started to explode.
Yes.
We're saying that even if you run that 100 times rather than 10 times, the SD would still have been the same? Or the SD would have trended down if you'd run it more times?
No, it'll still be high, won't it? The average will... The average will be going like this initially, and then it will settle down. Yeah, because each additional one will have less impact, but the standard deviation will still be high. So actually, the standard deviation exposes the instability of the results without having to do lots and lots of simulations.
There's another question, I think, Yanni.
Do you hear me?
I hear you.
Yeah. Okay. So this 80% is, let's say, the most interesting number. I can agree with that one. But we need to keep two things clearly separate from each other. One is the technical or scientific part where this 80% defines the saturation point of a lift system, right? So, so whenever you define a maximum number of people in the lift car, then 80% car load gives you the saturation point. And that's what the theory says. But then comes the interesting practical part, which is the debate. and then we come to the question that how many people really go into the lift. And it's behavioral stuff, yes. Someone thinks that 60% from the, let's say, rated capacity is enough. But then comes also the realism of designing lift systems. So you can always set the maximum wherever you want, low enough, so that everybody always will enter the car according to this maximum. But you will end up in huge lift cores. You can easily double your cores compared to what the current design practice is. So that's why there has to be some kind of like reasonable compromise. And now, for example, if you use this very, very classical approach from the 90s, okay, then you will get pretty much by assumption to the car. But for example, these ISO rules for selecting car, and based on mass, there's the note that if you use this 100% filling, you may end up in 2 full cars. And there's the recommendation for 80%. And this 80% actually is pretty close to your 0.21 square meters per person. So still, by just considering mass, you can bring down the number of people in the car by assumption.
Yeah, you're doing basically what I tried to do to Gina 20 years ago.
Yes.
Yeah.
But still you can do. And
yeah.
Even if you think that it's
I mean,
too much,
the oversized,
you can bring it lower.
Yeah, and this this we've already agreed that we need at least 2 bottles of wine to discuss this tonight.
Probably.
So Guy D went with this in 25 years ago, basically. But what I discussed with Gina was actually we used to design in the UK to 15%. Based on, so Strakos drew a graph which peaked at 12%, and then Gina redrew it and it peaked at 15%, and then that was picked up by BCA or something like that, and then we were designing this as 15%, and then when we got back to real world again and actually did some measurement, we found we didn't actually get up to 15%. It was very rarely went anywhere near 12, but 12 was sort of typically the worst case. I've seen more in China, but typically 12%. So actually, when we moved to area, we actually also said, we actually don't need to design, if we're going to be realistic about the loading, we want to be realistic about the passenger demand as well. So we actually brought that back. In the original British standard, it said 17%. So when I started, I was designing to 17%, assuming the cars were overloaded to make the calculations work. And it's just a mess. I just want to work based on what I see in the real world, and we had it earlier with where's BC our keynote speaker was talking about 1 per 8 or something in the morning. And that was loading. That's unrealistic. It's as soon as you can fiddle calculations any way you want, and you can mix up that. But I came to the conclusion that about 20 years ago, I was only going to design based on the evidence that I saw in front of me and I could measure. And if you want to change my mind, go and do the research. And if you're right, I'm going to change my mind.
Yeah, but still you can do it in many ways. So
We can do it in many ways, yeah. We can fiddle our results many ways.
Always fix
It comes back to that saying, there are lies, damn lies, and statistics.
Yes.
We're going to have to conclude at that point, I'm afraid, but thank you to our speakers for this afternoon.